All right, welcome back. So we're taking a look at Unit 10, Parametric and Polar Functions. First couple topics in Unit 10 will be the parametric equations, talking about how we can write them and how we can then apply them. And then the remaining portions of Unit 10 will be talking about the polar functions. So parametric equations are just another way we can describe what's happening. So for example, if we're talking about an object in motion being thrown in the air, generally we describe its vertical distance versus its horizontal distance. And then we have different time locations, but it's kind of tough to show all that on the same graph. So we can kind of break it into two separate pieces, a vertical versus time and a horizontal versus time components, and also put it together with the vertical versus horizontal component, which is kind of what you see in real life. You don't see the time, you see its location horizontally versus vertically. And that's what these three different graphs are showing us. First graph is vertical versus time, then horizontal versus time, and then our vertical versus horizontal. And they're all just, again, telling us a piece of the story, not the whole story necessarily. So parametric equations are one way to help show what this whole story really is. In this particular example, we're talking about comparing position with horizontally and vertically with respect to time. So from those graphs right there, you're creating these equations. You can see the rectangular equation, negative 2 over 225x squared plus x plus 40. Parametrically, the horizontal and vertical components you might recognize if you've been in some sort of physics class, especially the y component there. Negative 16t squared looks like your negative 1/2 gt squared, g being the acceleration due to gravity, and then everything else going with that. And we'll talk about that projectile motion in 10.2 and how it applies to the parametrics and rectangular. So the idea of the parameter is this, more often than not, this variable t, though it doesn't have to be a t. But a lot of times we're comparing these different ideas to time. So there's a time variable that's going to go with each of the different individual parts. A time variable to the horizontal, time variable to the vertical. And we can work with this and compare it back to rectangular form from parametric by solving for the time parameter. Now, whether we solve for the time parameter in the x equation or the y equation and then substitute into the other, just kind of depends on which one it's easier to solve for. So if we look at this first example here, obviously you have an x equation that's just t minus 2. The y equation has got 1 negative 1/3 t squared, 2/3 t, and 2/3. Clearly, it's easier to solve for t in the first equation. T is just x plus 2. And then we can substitute that into the second equation, where actually the first thing I'm doing is multiplying everything by 3 to get rid of my fraction. So it's negative 1 times x plus 2 squared, 2 times x plus 2 plus 2. Where when we FOIL out that, we get x squared plus 4x plus 4. Distributing gives us negative x squared minus 4x minus 4 plus 2x plus 4 plus 2, where when you combine those terms there, you're going to get a negative x squared. Negative 4x and 2x make negative 2x. Negative 4, positive 4 cancel, leaving just the plus 2. And then dividing the 3 back over, we get negative 1/3 x squared minus 2/3 x plus 2/3. Now, we don't have to get rid of the fractions like that in the beginning. I just find that easier to not have fractions while I'm trying to square out and distribute, so I just multiply the denominator over. If they all happen to be the same like they were, the 3 works out well. If they have different denominators, then obviously your least common multiple is what you'd want to go with, so you can get rid of all the fractions in one go. Now, in this particular parabola equation, we can see that the parameter is easier to solve for with the y equation, where if you subtract 3 and then divide by 3, you get t by itself. And in the top equation, they're all fractions with 5, so I multiply by the 5. And then again, I substitute my parameter y minus 3 over 3 in for t. And then kind of solve this out. So squaring the expression, again, we're going to go ahead and FOIL the y minus 3. Get y squared minus 6y plus 9. And then 3 squared is 9. And then when we distribute the number on the outside multiplying inside, you'll find the 9s cancel each other. And then the 6 reduces down to a 2 because it cancels with the 3. So we really have a y squared minus 6y plus 9, and then 2y minus 6 minus 9. That allows us to combine the y terms. Negative 6y and 2y is negative 4y. Positive 9, negative 9 cancel, so it just leaves the negative 6 behind. And then dividing the 5 back, we get 1/5 y squared minus 4/5 y minus 6/5. So you're going to find what we're doing here is we're just rewriting these parametric into rectangular. We're going to kind of go through our conic equations. These were clearly parabolas with the parameter. Now they create a parabola rectangularly. This one was horizontal. The other one was vertical. We'll also talk about the ellipse, hyperbola. We're not really going to do an example of a circle per se, but a circle is really just an ellipse where a and b are the same number. So an example like this right here, this is going to create an ellipse. And it would be a circle if instead of being 2 cosine and 3 sine, they're both like, 2 cosine and 2 sine. Or 3 cosine and 3 sine. They were the same number multiplying in fronts. And the reason why this creates an ellipse, because you can recognize sine squared plus cosine squared equal to 1 from your Pythagorean identities back in Unit 7. So the goal here is, because we really can't isolate t because it's part of a trig function, but instead we isolate the trig function itself. So we add 2 and divide by 2 for the cosine portion to get cosine by itself. And then we add 5 and divide by 3 to get the sine by itself. The angles, as long as they're the same, it doesn't matter what they are. So they're both 2t, that's great. If they're both a fraction, as long as it's the same fraction, that's all that truly matters. If they were different angles, then this wouldn't work then. But sine squared, we're going to leave the expression to be squared, but we are going to square the denominators because then we can recognize this. It looks exactly like our ellipses from Unit 8. So this would be our vertical ellipse because the value underneath the y was larger. We'll find this would be a horizontal ellipse because we subtract 7 divided by 4 for the x to get sine by itself. And now here we'd subtract 5 and divide by 3 to get the cosine by itself. Again, the angle is the same, so it doesn't matter what the angle actually is. Sine squared would be the x minus 7 squared over 16. Cosine squared is y minus 5 squared over the 9. And again, this would be a horizontal ellipse now because the fact the horizontal value is larger. And like I said earlier, these could be circles if they were the same numbers in front, multiplying with your sine and cosine, because then you're dividing by the same number and it will create the equation of an ellipse, a circle rather than an ellipse. Now, the hyperbola is based on secant and tangent because an alternative formula for the Pythagorean identity sine squared plus cosine squared equals 1 is secant squared minus tangent squared equal to 1. And that's where the hyperbola comes into play because it was your two fractions subtracting. And before it didn't really matter because like if you look back here for a second because we're adding, I could have easily said the y minus 5 squared over 9 plus the x minus 7 squared over 16 because we're adding. It's a, the order doesn't matter when we add, but when we subtract it does, so we have to make sure we're careful. We have to make sure the secant portion goes first. So we're subtracting 3 and dividing by 7 to get secant by itself. And on the other side, we're subtracting 1, dividing by 4 to get tangent by itself. And again, the secant expression has to go first, so this would be a horizontal hyperbola because the x fraction is positive and the y fraction was negative. And these are actually kind of nice in terms of like actually trying to graph the hyperbola and the ellipses on your graphing calculator because since your graphing calculators have it as a function table, so like y equals or f of x equals, you really can't properly graph ellipses or hyperbolas because it's not a y equals equation. It's an implicit equation because the y is in the middle of it. But if we put it as a parametric equation instead, you can graph that as long as you change to the parametric mode. So if we look at this last example here, so now when we subtract the 5 and divide by 8, that's how we get the tangent by itself. And then if we do the same thing with y, we're adding 2 and dividing by 3, we get the secant by itself. Now the y goes first because it's secant squared minus tangent squared. So this would be the example of our vertical hyperbola. And there's that, the equation right there. So just simply a few examples of rearranging your parametric equations into a rectangular form, connecting it back to your conics. A lot of times it really is going to be the parabolas, and that's what we're going to focus a lot on with 10.2, which is going to be a practical application of the parametric equations. So I'll see you guys next time for that.